The future of AI is not just built by the people who create models, right? They're definitely important, but it's also built by the people who actually make the AI models accessible as well. Once you have like a big model, actually serving the model, making it accessible to a lot of users is a very difficult system problem.
My guest today does exactly that. He works on the software that turns a raw pre-trained model, the kind that just predicts the next word, into ChatGPT, into Claude, into the thing you actually use. That process is called post-training. And that's where the real work now happens. His name is Anish Mahishi. He started with a course on Coursera in the second year of college. He's been a data scientist at Fractal, done medical MRI research at NYU, interned on the PyTorch team at Meta, spent 3 years at Bloomberg, and 2 months ago, he joined NVIDIA on the NeMo-RL team. On this episode, what post-training actually is, why he thinks evaluations are the most underhyped idea in AI, why fully autonomous agents are overhyped, and the one piece of advice for high school students that has nothing to do with AI at all. I'm Satvik Subramanian, founder of Wise in AI. This is AI Innovators High School Edition. Let's get into it. Hi Anish, welcome to the show. To start, and I always start here, can you tell me how exactly you made your way into the world of AI?
Hey, Satvik. Glad to be here. Thanks for inviting me. I think it all started back, I think, in 2015 when I was in my second year of my undergrad. Someone introduced me to Coursera for some reason, and I stumbled upon this Andrew Ng's machine learning course. I think it was popular at that time. The phrase machine learning, it sounded very catchy at the time. I'm going to make machines learn. Is that the idea? And then I eventually, sort of delved into the course. And then, I think it was a great learning experience. And subsequently in that year, I was actually interning at a company. I got to work on, computer vision and stuff. So I think it was a pretty interesting experience for me. And then I think I was, in touch or working with AI after that.
Cool. Your undergrad was in computational and applied mathematics at IIT Delhi. And it's a math degree, not a computer science degree. So do you think starting from the math side gave you a different advantage getting into the deep end of AI systems?
So the name of my major was called Mathematics and Computing. So it was it did have computer science courses, but we did a lot of math courses in general. So we did, math courses such as we did a lot of linear algebra courses, topological spaces, probability. We also did a couple of courses on numerical computing. So those were all pretty interesting. At that time, I was more inclined towards doing more of computer science courses, but I do think that the math courses that I did was very helpful. I think it provided me with good foundations to grasp the machine learning concepts easily. I wouldn't say advantage as such, but I think I was maybe slightly ahead than others in terms of like understanding the stuff behind. Yeah.
Yeah, personally, that's good to hear because I'm more of a math kid, but to hear that it gives you a slight, maybe not advantage, but as you said, it gets you a little ahead. That's nice to hear.
Definitely.
Yeah. You've had a pretty interesting career shape, data science at Fractal, and then NYU for the master's while doing the medical MRI work at NYU Langone, and then interning on the PyTorch team at Meta, then a machine learning engineer role at Bloomberg, and then now the post-training team at NVIDIA. So every one of those is a different lens on AI. So I wanted to ask you, what did each step teach you that the last one didn't?
I think overall, I feel it's a very diverse background, I got a chance to, touch different components or apply AI to like different domains. So I think at Fractal, I was a data scientist, and then we usually applied or developed machine learning models to solve business problems. And one of the exciting things there was you actually got to test your models in real time, and actually you could actually associate like a dollar value to that, to your model, right? How much impact within, in terms of dollar value is your model providing? That was, pretty exciting to see that, you know, to see the value that we were adding to the company itself. I think it was a very great learning experience for me in terms of developing machine learning solutions in terms of improving the business, for example, right? I think after that, I went on to pursue my master's at uh, NYU. And I think during my grad studies, I was involved with the research group working on MRI imaging. So the professor that I worked with was part of Courant and Langone. So I think it was the first time that I was actually conducting research. I had never done research before. So, and plus, I think it was on medical AI, which I think is a whole different ballgame altogether. You need your models to be trustable and robust to sort of deploy them. But I think applying AI to medical field was pretty challenging, but as well as a refreshing experience for me. At the same, I think during my NYU days, I also got a chance to intern at Meta. Was fortunate to be on the PyTorch team. We worked on model compression and quantization. So I developed some libraries for in the domain of sparsity. So I think this was more related to AI infra, and that was something that I had never done before as well. So I got to learn the importance of developing the infrastructure altogether, writing good documentation, creating a friendly developer experience, right? So that's really important to advance the field of AI and in open source altogether. And I was at Bloomberg for 3 years. I think there I worked on search and retrieval, and I think one of the important things that I got to learn there was uh, what are the challenges that goes into like deploying models in at a real production scale, right? You need to, it's not just a model itself. You need to look at observability, scalability, reliability. A lot of software engineering goes into maintaining such stuff. I think it's been about 2 months after I joined NVIDIA. I think I've been working on NeMo-RL. So my team mostly develops the infra and optimizes the post-training systems around LLMs. I think one of the important things that I'm learning in here is, how do you actually scale models to a lot of GPUs, for example? How do you write efficient, piece of software that can, train models such that your GPUs are not idle, right? So I think it's been a pretty exciting couple of months so far, and I'm looking forward to more of it in the coming months.
That's nice to hear. Yeah, I mean, it sounds like a very engaging career path. So that's how I would describe it. But yeah. So now I just wanted to pivot to post training from the inside. So I wanted to start with something most people don't actually understand. When someone opens ChatGPT, for let's say, for example, and they type in a question, what happens between the moment that they hit enter and the moment that the first word shows up on their screen?
So when you open, ChatGPT and then you type in a prompt, right? Let's say, what's the who won the World Cup match today, right? So the phrase or the question that you typed in is called a prompt. So now when you hit enter, the the request, let's talk about the request journey, right? So initially, I think what happens is, the request is like scanned for like, things like rate limits, for example, right? And it goes through a lot of boilerplate stuff in the beginning, you know, and then I think you also sort of see if the text is like, safe or not to actually even proceed to the next step. And then after that, I think we get to the interesting part. Also, like, just a quick disclaimer, like like the system itself is like pretty complex. This is like a 10,000 foot high level overview of what happens uh, in the journey of a single request in ChatGPT. Now, let's get to the interesting part. So essentially what happens is when the request goes and hits the model, the prompt that you typed in, it needs to sort of get tokenized, right, into a stream of numbers. So LLMs, they don't understand words. It doesn't understand English. You need to sort of, translate that into a representation, a numerical representation for it to, understand and produce answers. So that step is called like tokenization. So, you can think of tokens as, words, for example, right? So it's broken down into like words, and each word is like associated to a number. And then what happens is that it goes through the model itself, right? So it goes through like several layers of the model. And then what happens is that it starts generating the output, right? So it doesn't generate the text all at once. So it starts generating text or words or tokens, for example, one by one, right? So you call that order regressive, right? So all these LLMs are order regressive. So because it generates output tokens one by one, right? So once these tokens are sort of generated, the floating point or the number itself is sort of mapped back to a word, for example, and then it's sort of streamed to you, right? So when you hit enter on ChatGPT, you immediately start seeing word by word appearing instead of like everything at once, right? So that's most likely sort of related to the order regressive fashion in which these models process. So you start generating tokens or words one by one. And there might be some additional things that might happen, based on the user's request, like, doing a web search or doing some, you know, calling a tool, for example. But so like overall, it's a very complex system altogether, but this is, just like a 10,000 foot high level overview of how things work.
I wanted to talk about the part of the work that you're actually doing today. So most people think about training as just one thing. You feed a model a bunch of text and it just learns. But there's actually a whole second phase called post-training that turns a broad pre-trained model into ChatGPT or into Claude or into anything a person actually uses. And so you just joined the NeMo-RL team at NVIDIA. And so can you explain what exactly post-training is in plain English and what exactly your team builds?
For sure. So let's start with what pre-training is, right? So when you pre-train a model, let's say you have like a bunch of text corpus from Reddit, for example, or any place from the internet, right? So what you're essentially doing is giving a piece of text to the model and asking it to predict the next word or the next token. So you could scale this to the entire internet, for example, right? Because you're just trying to predict the next word conditioned on, whatever context or whatever words were behind that particular behind the target word. Now, great. I mean, now you have a model that, it's got like pretty good knowledge, right? But it's still not useful, right? Because all it can do is like complete like the next word in a sentence, but it doesn't really know how to, for example, follow instructions or, you know, go and use a computer or, solve a math problem, for example, right? So suppose the idea of post-training is, centered around making the model actually behave like a good assistant, right? So it could be, trying reinforcing it to output, safe text, for example, right? Abstaining when if a user asks a harmful question, making it use a computer, for example, or or even like going and solving like a complex math problem, for example, right? So at NVIDIA, I'm on the NeMo-RL team. So NeMo-RL is like an ecosystem that or library, for example, that you can use to like post-train the model. So it contains like, efficient implementations of algorithms. You can scale it across, thousands of GPUs without you having to worry about the internal details and just focus on the algorithm. So that's more about NeMo-RL.
And then there's this whole alphabet soup of post-training algorithms, RLHF, DPO, GRPO. For listeners that are listening, they are all different ways of teaching a model what a good answer looks like using human or automated feedback. So can you walk us through what each of them is really solving and where you actually land? Which one wins for which kind of problem?
So let's go back to, the whole setup again, right? In the stage of pre-training, what you usually have is, you have an input and a target, right? You want to train the model to output a certain target. Now, in the post-training phase, right? Essentially, you would want to reinforce the model to an output that is most useful, right? So that's the entire idea of post-training. Now, coming to these, you know, different flavors of post-training algorithms, right? Let's start with, RLHF, right? So RLHF is, it's called reinforcement learning through human feedback. So essentially what that does is, essentially the setup is as follows, right? So you have an input text, right? And then you ask model to produce like two outputs, right? Now a human actually prefers one output over the other. Now using this sort of feedback, you actually reinforce the model's weights towards the output that was actually preferred by the human, right? So, in practice, we people usually have or train a reward model separately. So they train something called as a reward model that sort of approximates a human's preference, right? So you don't have to like go and ask a human every time to like choose A versus B. You have like a data set already curated. You train a model on that. Now you use that model as an approximation to to sort of understand which model is better or which generation would a human choose or prefer. So now the idea becomes maximizing the output provided by your reward model. So and it's done through like reinforcement learning in general, and it's very expensive, right? RL is super expensive compared to like a supervised training paradigm. So DPO is called direct preference optimization. So what they do is, it's the setup is pretty much the same, but they sort of simplify it by taking out the entire RL, taking out the RL setup itself, right? So they formalize it as a supervised learning algorithm, and then they sort of train it, and it's much more cheaper and provides, competitive performance or accuracy compared to RLHF. And it was pretty popular, about a couple of years ago. Um, I think the most popular one now is GRPO. It's called Group Relative Policy Optimization. The idea behind that is, now all you now know is, RLHF and DPO sort of solved what output would a human prefer, right? But what about the tasks such as, solving a math problem, for example, right? Those are something that a human, fine, like they can prefer, but that's something that can be automatically verified. You can sort of build like a simple text matching algorithm that can check if the output generated by the model contains the answer or not. So, formally that particular training paradigm is called reinforcement learning through verifiable rewards. So essentially, training the model, you don't need like, a special reward model, for example, but you can just verify the output automatically. So now if you can do this, you can scale your, training such that you can, generate it. You can train your model over, billions of generations, for example, right? So that was the main idea behind GRPO, and essentially the setup is you ask the model to like generate outputs, right? And essentially a group of outputs, and then essentially each output of that group is sort of scored and verified and assigned a reward, and then you tend to like move your weights towards the generations that was actually that had accumulated higher rewards, for example. So I think it's definitely like hard to say which one is the best and which one is not, because previously it was RLHF. I think RLHF used this flavor of reinforcement learning called PPO, or proximal policy optimization. And, people started doing DPO, and then GRPO was famous for a while. And then I think some of the recent models now actually use PPO again, and they're able to get like really good results. So it's like really hard to say which one is better right now. But I do think that, learning from feedback is a pretty important aspect of making a good AI model.
So for my next question, I think you have a pretty good vantage point, a very specific one. So DeepSeek's R1 recipe opened up reasoning model training, which showed that you could get a model to think for a long time by rewarding it for arriving at correct answers on verifiable problems. And so from a post-training systems perspective, what actually changed about how these workloads run?
So the the setup here is that you don't have like a static training data set, right? And in a supervised learning setup, what you have is like you have like a sample. I mean, you have like a static training data set comprising of input and output, right? And then you sort of train them all over again, right? You train it over like multiple epochs, for example. In the case of post training, what you're doing is you're sort of asking the model to like generate multiple generations, and then reinforcing it to behave more towards the weights that actually produced like generations which got like a higher reward, right? So essentially you do that over multiple times, right? Like, so you generate and then you train the model, you generate and then you train the model. So there's of course like a step wherein you verify and assign rewards to each of the generations. So now you can imagine that, like you're essentially training the model on its outputs itself, with the caveat that it produces like a higher reward. Now let's talk about, like the infra side of things as to like what it takes to actually make this work. Uh, So now you've got like two phases, right? You need to like generate outputs, or formally we call this rollouts. So we do rollouts or generate multiple groups of generations, and then we train the model, and then we generate, and then we train the model again. So now you can see that there are like two phases, right? There's rollouts, and then there's training. Now, when you do these two things together, you need to sort of juggle around with, synchronizing both the workers, right? You need to make sure that they're using valid weights, right? You need to make sure that the GPUs are not idle, right? So usually what happens in like these vanilla post-training algorithms, when you do generation, your training GPUs are sitting idle, right? And when you train, your generation GPUs are sitting idle. So there's that GPU efficiency as well that we need to manage. So I think overall, like post training is more about, it's very systemic in nature in the way that you need to juggle around between multiple things, and it's sort of not easy to make it work and make it more efficient. So, there are like certain algorithms that, that sort of optimize and make the system more efficient, but I think there's still like a lot of gap to close.
All right. Just want to pivot to now. I want to pivot to emerging trends in the field. So where the field is going. And so everyone's been talking about agents, everyone in the industry. And so I wanted to know from an infrastructure perspective, are agents actually a fundamentally new thing? Or are they just a UX pattern on top of the same models that we already had?
So let's take a step back and talk about just models, right? So in a vanilla large language model, what happens is that you give an input text, right? The model starts outputting tokens and you get to see those tokens, right? Now that was the older paradigm, right? So the model did not have actually access to any of the tools or computer, for example, right? So now agents inherently have access to a lot of tools. And how do you actually make that work? Because all your large language model does is it outputs tokens, right? Now, how do you sort of make it call a tool, for example? So the way that it happens is you want your model to use a calculator app, right? You want it to do some calculations. Now, what it takes to do that is that the model needs to know that there's like a calculator app, and then you give it like an API schema using which you can actually, you ask the model to like spit out text, which is like a request or a call to the calculator that you can actually like, execute, right? So essentially, you ask the model to like output certain things that can be called. And then there's like an execution layer on top, right? That you can execute to get the output from the tool. And then essentially the output of the tool goes back to the model. The model's just like, waiting for the tool output to come back. And then, there's like to's and fro's. So the high level idea is that it's not like a UX layer on top, right? There's like additional execution layer that sits on top, that actually needs to sort of execute the code and stream the outputs back to the model and take inputs from the model to execute things. So I would say it's more like a more of a computational layer on top rather than like a UI UX layer.
Okay. So now I wanted to pivot to the quick fire section. So basically just whatever's on your mind, just say it. Number one, what do you think is the post-training technique that will still matter in 5 years from now?
I think it's hard to like zone in on like one post training technique since I mentioned that things become popular and then an older algorithm becomes popular again. So it's sort of hard to predict that. But I think in general, training a model using its feedback, it could be human feedback, it could be the AI model's feedback itself. is going to be really valuable in the future.
Okay. What about the most overhyped idea in AI right now?
I think some of the things that I'm hearing is fully autonomous agents. I think we're not there yet. I think agents can solve like smaller horizon tasks, smaller tasks, but I think a longer horizon task is still, it's still far away. There's like a difference in terms of asking a model to, write up something for a demo versus actually making it work at production scale. So I think fully autonomous agents are a bit overhyped right now.
Now to the other side of the spectrum, what do you think is the most underhyped?
I think evaluations are underhyped. A lot of folks in AI tend to, not worry a lot about evaluation. I mean, they do evaluate, but when you have a product or when you have an AI system, it's not just about the benchmark numbers. It's about how much useful is your model to your users, right? It's not easy to actually capture that. So you need to have a good mechanism of actually, measuring how well your system performs in general in terms of users. So I think evaluations are very underhyped.
Okay, now on to reasoning models. Do you think it's a real breakthrough, or do you think it's just an expensive trick?
I think it's a real breakthrough because if you think about it, it's exactly how human brain functions, I think. So if you ask an easy math problem to a human, there's just gonna instantly spit out the answer. But if you ask like a hard complex problem, you actually think, right? You think, you emit thinking tokens internally before you actually come to an answer. So I do think that it's a real breakthrough. It is expensive, but I think it's still a real breakthrough.
Okay. What's your take on AI in medicine, given all the research that you've done?
I think AI in medicine is a really hard problem to solve, right? I don't think it's matured yet, like it's matured in a lot of other domains. I think it's really hard, to make your model robust, right? Because, it's a matter of a life of a person that you're giving the AI to sort of, access to. I feel that we're not there yet. It's a very hard problem to solve. You need your models to be robust and trustable. And plus, I think there's like a data issue as well. It's not easy to obtain like medical data to actually train your models. So like a lot of data are, are private or it's not accessible, and there's a lot of privacy concerns as well. So I think that comes into play as well. So overall, I believe that it's a really challenging problem to solve, but it's going to be really impactful that if you can get it to work.
One skill that's not coding or math that you believe has mattered more to your career than you would have expected initially?
Good question. So I think I would say, a couple of things, right? So I think one is definitely talking to people, right? Communication. I think understanding the problem from another person's perspective actually, you know, it gives you a lot of insights. And for that matter, I think even if you want to, let's say, understand a difficult concept, explaining that concept to another person or explaining it to yourself even has been really, really helpful for me. And, like, don't be afraid to ask no questions, right? I think like, if I was scared of asking no questions, I don't think, things would have gone sideways for me because, you get to learn a lot. I think the second thing that was pretty much important is important is like, don't shy away from hard problems, right? It could be, you might not be, the worst thing that can happen is like you might not be successful in solving it. But I think the learning experience in itself is so much valuable that, right? It's you try to take on much harder problems in the future and more important problems in the future. So I think those are the couple of things that I think are pretty important for me.
Okay. Last, maybe one or two questions. Okay. So, me as a founder, I just want to put that hat on and ask you or tell you about my startup really quickly. I have a startup called Wise in AI because I noticed that older adults carry decades of judgment and knowledge that they've acquired throughout their lives that today's tech doesn't really meet halfway. And a huge practical constraint for me is that the models have started to run on devices that older adults actually own. So, like laptops or an old iPad or a phone, not a data center. So, from your perspective inside NVIDIA, is on device AI actually going to work at the level a founder like me needs? And what do you think the timeline is for that?
That's a good question. I think I think it's it really depends on the it's really dependent. I wouldn't think of it as on-device AI versus non-on-device AI. I believe that on-device AI, like you for example, you can't go and serve a frontier level model on device, right? So if your task is such that if a right sized model can actually solve it, I think, and can be deployed, you should go ahead and do it. I believe that we've come a long way in terms of actually running models on device. There are things like quantization and distillation, for example, that can actually make your model work on edge devices. So I would say that, it definitely looks promising in the future. And I don't have like a certain timeline in my mind because I haven't really worked on like deploying models on device. But I think the only thing that that we can sort of predict is that it's definitely gonna get better as we move forward.
Okay, thank you. Final question. There is probably a high schooler listening to this right now who thinks that the only way to do meaningful work in AI is to train the next big model. But your career says something different, that the plumbing matters just as much as the palace. So the person that makes AI fast is just as important as the person who makes AI smart. So what is the one sentence that you would want them to walk away with?
I think what I've learned is that the future of AI is not just built by the people who create models, right? They're definitely an important part, but it's also built by the people who actually make the AI models accessible as well, right? So I would, you know, uh, that would be my sentence. But just to like back it up, I think once you have like a big model, like, actually serving the model, making it accessible to a lot of users is a very difficult system problem. And it requires knowledge from a lot of different, you know, concepts, right? You need to know computer architecture. You need to know how GPUs work. You also need to know how the model works in itself, because the way that you parallelize the model is closely dependent on how the architecture looks like. on top of that, you also need to handle the observability and reliability aspect of things. So I believe that, a large portion of making things work is definitely plumbing.
Okay. Thank you so much, Anish. This has been a really rare look under the hood of AI, so I really appreciate you making time for a high school podcast.
Thank you so much for having me. This was a really nice experience for me as well. And I hope people do find this conversation useful.
3 things I'm going to keep thinking about after that conversation. 1. The alphabet soup finally made sense. RLHF, DPO, GRPO. All different ways of telling a model what a good answer looks like. Anish's honest verdict was that there is no clean winner, which means the thing that actually matters is not the algorithm, it's feedback. 2. His answer on medical AI. He said it's a matter of a life of a person that you're giving the AI access to. It's not just accuracy, it's stakes. 3. His advice for high schoolers. Don't be afraid to ask newbie questions. Don't shy away from hard problems. Explain the concept to someone else if you actually want to understand it. That is not advice you can only use in AI. That is advice you can use tomorrow morning. Show notes have links to Anish's MRI paper, the MedMarks benchmark suite, NVIDIA's NeMo-RL framework, and the Coursera course he's first started with. If you're a high schooler building something with AI, send it to me. I read everything. I'm Satvik Subramanian, founder of Wise in AI, and this was AI Innovators, High School Edition. See you next week.